Substances require an exchange of energy into the system that substance is in or out of it to either heat up or cool that substance and make the temperature change. Furthermore, to change a state of an object from a solid to a liquid or to a gas or back the other way also requires an exchange of energy. And it is at these changes of states between solids, liquids, and gases that a lot of energy is required to either be absorbed endothermically to move in this direction or to be shed exothermically to move in that direction. What we're looking at today is a commonly used image known as a phase line or phase chart that shows how a substance can move across states and at points where changes of states are happening. The one that gets studied the most, of course, is water, and that's what we'll be looking at today. So water has at normal pressure has 0 degrees and 100 degrees as its respective points where we're moving in phases across solids, liquids, and gases. And for this to happen, we have to have the energy investment in joules. Through countless years of experimentation, these standard values have been derived by scientists, which is very useful in industry, amongst other things, towards working out how much electricity or other forms of energy, say a chemical plant or a manufacturing plant, are going to need to bring up or bring down substances to a desired state or to a desired temperature. So we have, let's say we're moving in this direction from lower energy to higher energy, from solids to melting to liquids to boiling to eventually to a gas. So water, let's say that it starts at a solid. We have a block of ice. Let's say that we're moving from -8 degrees Celsius and we're going to warm it up to 19 degrees Celsius. How much heat energy at minimum will be required? And of course, this is assuming there's no losses, and we know in the real world that's not going to happen, but this at least sets a baseline of what's required. So at -8 degrees, that's less than 0. So we're solidly in the solid zone, and we're going to finish in the liquid zone because 19 degrees is between 100 and 0, putting it in the liquid phase. So we start in the solid phase and we will move to the liquid phase. So this requires an energy investment that it follows 3 different standards depending on where we are in the heating of this block of ice. So as we know, based on a calculation that's found in your reference sheet, is that if we are at a particular phase of a substance, then the amount of energy in joules that is required to heat or cool that substance is the substance's mass times a constant value, depending on what phase we're in and what the substance is, and the change in temperature. Now, it is arbitrary whether we are heating or cooling, the amount of energy investment will be the same. So we have, in the case, some solid ice here at the beginning, and we have a mass of 250 grams of it. We're going to the point of melting, which would be from -8 to 0 is a change of 8 degrees, okay? At this point, we're not concerned whether it's negative or positive. We'll worry about that later. And so let's say we have heated up this block of ice. That means we had 206 joules for every gram, for every degree that's changed, times 250 grams, times a change of 8 degrees. And so that turns out to be a total energy investment of 4,120 joules. Now it's time to actually melt the substance, and this requires a lot more energy because we're trying to weaken the bonds between the water molecules and that crystal lattice that we call ice. That takes energy. So we are looking at 334 joules times, once again, it's 250 grams that we are heating up. But notice I have an X here. When we're at the point of heat of fusion, which is the point of melting or freezing, there's no temperature change happening. So a change of state does not actually involve a temperature change. We're simply at that at that melting or freezing point. So we just simply multiply this number times this number, and then this becomes another energy investment of 83,500 joules. And so as we can see, it takes a lot more energy to melt something than just simply heat it up as a solid. Then finally, we have now melted it. And so we are marching further to the right here in heating it up from 0 to 19 degrees. So that is a change of 19 degrees as a liquid for this 250 grams. And the specific heat of liquid water is 4.18 joules. So if we multiply these three values times each other, this becomes another energy investment, as that is 19,855 joules. So when we add these three together and sum them up, we have a total of 475,000 joules. And notice that I've put a positive symbol because this is endothermic. We have added energy to this system, which is a 250 gram block of ice. And that is what is making it possible first to heat up the block of ice from -8 degrees to the point where it's ready to melt. Then we have to put a whole bunch more energy in here to actually make the melting happen and to weaken those bonds between the molecules, make them energetic enough to exert something of an independence that we would view as, basic motion. It moves around if we shake it. It'll flow if it's spilled. And then once it's become a liquid, we are warming it 19 more degrees. So the composite amount of energy investment for the entire change, that being that block of ice at -8 degrees, is to 19 degrees Celsius is this amount. If we were going to go ahead and keep heating this up all the way to steam, we would of course have to bring it all the way to 100 degrees, and then we come to what is called the heat of vaporization. And as we can see, that requires far more energy than at any other point in the process, because at that point, when we're transitioning from a liquid to a gas, that means the water molecules are so filled with kinetic energy that they exert no actual attraction to each other. In other words, they just collide with each other, and their collisions are elastic. They don't exhibit any sort of attractive force. To have that amount of independence from each other, these molecules must need to have a lot of energy, and it does. And then if we wanted to heat this block of ice that's been made into steam further into heating up a gas above 100 degrees Celsius, we actually drop once again. So as you can see, when we're heating or cooling a substance while it's within a state, it's really not that much energy per gram. However, when we are changing states, the amount of energy that is required is significant. Now think of this in reverse terms, however. Let's say that we were moving from 19 degrees and we're cooling it, and we're taking it back down to -8 degrees Celsius. So we're freezing it. We're moving in this direction. It will be the exact same amount of energy. However, we have to get rid of it, and this is called exothermic. And when we are deliberately cooling a system, another word for this is refrigeration, of course. So we can have the outside cold weather do it, or we could stick the 250 grams of water into the freezer, and then we come back later and it's frozen back into the block of ice. But just to restate, these values are the same regardless of whether we're going in the heat into the direction of increased kinetic energy and warming or decreased kinetic energy and cooling. We just simply put positive or negative depending on whether we're endothermic or exothermic in our physical change.